Hi everyone. Here we go. We are starting chapter 1 in our pre-calculus book. It is on functions and graphs. So this first lesson 1.1, we're going to look at some mathematical modeling and just some basics with solving a variety of equations. And then we will get into functions for pretty much the remaining lessons in this chapter, just kind of looking at a variety of functions and their properties, inverses, and transformations as well. So for this first lesson, 1.1, modeling and equation solving, we basically just, start out by saying if we want to look at real world problems, which is really the point of all of our learning, we have a lot of tools to help us with mathematical modeling. Some of the more common models are numerical, algebraic, and graphical, which are those three are the title of your textbook on the front cover. So the first one they introduce are numerical models. So this would basically just present itself as a bunch of data that you look over and try to make some conclusions. So often it'll be in the form of like a table of values. You look for patterns within those values or any kind of discrepancies, maybe numbers that don't really fit the rest of the data, like outliers, things like that. So I would encourage you at this point to look at example 1 and example 2 in the textbook. I didn't include them here because they just did a nice job in the book of laying out a couple examples of scenarios that have data tables and just kind of explaining how you would go about kind of making some conclusions from your tables. So go ahead and take a look at those two examples. And then we'll get into the next model, which would be an algebraic model. So for those, you would relate quantities or variables using formulas. So this is our basic algebra where we can use or create a formula for data, and then we can then use that formula to generate unknown quantities by relating them to the quantities that we do know. So that brings us to example 3 with delicious food, pizza. So we're looking at two different types or shapes of pizza, we should say. So first we have a rectangular pizza, 20 inches by 26 inches. It's the same price as an extra large round, which is a 26-inch diameter. So if they're the same thickness and same price, we want to figure out, well, one size might give you slightly more pizza than the other, or one shape. So just trying to figure out, like, how do we get the most pizza for our money? So this is a pretty simplistic problem where algebraic models would be perfect because we can use formulas to find area of the rectangular pizza, area of the circular pizza, and then just compare the two areas. So let's do just that. For the rectangular pizza, we could use the area equals length times width. So our length is 20 and our width is 26, or vice versa, doesn't matter. So that would give us 520 square inches of delicious pizza. Let's switch the colors here. For the round pizza, our area would be pi times r squared. So notice they did give you the diameter, so just make sure you are not substituting in 26. You're using half of the diameter, so we're going to use 13 for our radius. And then I would suggest just in your calculator, as you calculate that out, to keep values as precise as possible. If you could use the pi button, don't use 3.14 because that's just a rounded version of pi, so you're going to have an answer that's slightly less accurate. Not a huge deal, but we always want to have our, increase the accuracy of our answers as much as possible when we're working on math problems. So this one, we could probably just round to the nearest one to kind of match the rectangular answer. So about 531 square inches, which tells us if we want more pizza, we should buy the round one. by the round pizza. Done, using our algebraic models. All right, so the third mathematical model introduced in the book would be a graphical model, which is just a visual representation of a relationship between variable quantities. So how do your two variables relate to each other using like visual cues to kind of help you understand that? And this is straight from your book. It says learning to interpret and use graphs is a major goal of this book. So we're going to be looking at a lot of graphs. A lot of real world scenarios. The first thing we do is try to take, data and graph it and see visually if it looks like any kind of function that we could then use an algebraic model to represent. If we could create an algebraic model, we can use it like it mentions above to generate, unknown values. So example 4 in the book actually mentions Galileo's gravity experiments. He spent a lot of time rolling balls down inclined planes and then recording the distance they traveled as a function of elapsed time. So this is a really common topic that crosses a couple different curricular areas. So for example, physics. If you've taken physics or are taking it this year, that'll probably be something that you look at. And not only that, when we get to our last chapter towards the end of the year, which is an introduction to calculus, we're going to be revisiting this exact scenario. So we'll come full circle. All right, so in example 4 in the book, there is a table of all this data. So this is provided for us. And we want to know what graphical model fits the data and if the data can be represented by an algebraic model. So I already graphed this in Desmos and provided that right below this table of values. So it definitely looks like it has a curve to it. As the elapsed time passes, the distance traveled also will increase, and looks like that amount that it increases keeps growing, which is why it's not linear. So curved models would be the most common ones, probably exponential or maybe quadratic. Maybe this is the right half of a parabola. Just a couple different options. So we're going to kind of explore it a little bit. Maybe we'll start with the idea that it could be exponential. In order to verify that, we can go ahead and try to create an algebraic model of an exponential equation. So I'm going to just kind of label on the side here. We are going to use maybe t for time and d for distance. And if we're keeping a pretty simple exponential equation, we could use d equals some constant raised to the t power. This is a pretty simple model. It goes through 0, 0. There's no vertical shifts that we have to worry about, anything like that. So in order to test this out, we're going to have to choose an ordered pair from our table. So it's up to you what you want to choose. I'm going to go with 2, 3 because there's some nice integer values. So for a distance of 3 inches, we want to know what k needs to be raised to the second power, t equals 2 seconds, to give us that ordered pair. So it would be real quick to solve because I would just need to take the square root on both sides. And if I do the square root of 3 in the calculator, and then we'll just round it maybe to the hundredths place, about 1.73 would be like an approximation for our constant k. So just taking one ordered pair and plugging it in to get your constant, which would then give you an algebraic model of d equals 1.73 to the t power, that's a good start, but you need to actually test it to see if it generates the rest of the points on this function, because if it doesn't, that's going to indicate this is not an exponential model. So if we go ahead and just pick another point, well, I don't know, let's jump to the last one, 848. Let's say, all right, if we want to travel a distance of 48 inches, we should be able to get that by doing 1.73 to the 8th power. So if I check that, 1.73 to the 8th power, that's about 80.2, which is definitely not equal to 48. So our attempt at using an exponential model failed because it's not going to generate the other points. So at this point, I would say let's abandon the exponential model and let's try a quadratic. So our basic quadratic equation that we've kind of been reviewing, y equals ax squared plus bx plus c. Again, if we just kind of manipulate that a little bit, we don't have a vertical shift that we have to worry about. Our y-intercept is just 0. And then our axis of symmetry would also be going through 0. So really, we would just try to come up with an algebraic model of y equals some sort of constant times our independent quantity squared. So if we change it to the variables in this problem, we would say d equals k times t to the second power. All right, so if we go and test that out, let me grab another color for that. I'm going to use the same point again of 2, 3. All right, if I'm going to plug in 3 for the distance and 2 for time, I can then go ahead and solve that. So we'd really have 2 squared is 4, so 4 times k. And then if I divide by 4, that means k is 3/4 or exactly 0.75. So again, that's my constant. So I can come up with my algebraic model of d equals 0.75 times t to the second power. So that's my quadratic equation as our algebraic model. And again, if we want to test other points and see if this actually generates the other ordered pairs in our table. So I'll go ahead and use that same one, 848, which will be a little consistent here. So for a distance of 48, it's 0.75 times 8 to the second power. That would be 68, and then 3/4 of 68 would indeed be 48. So that looks good. You would want to probably check the rest of, or at least the majority of the rest of your data values, but you would see that that algebraic model will generate, oh, sorry. The algebraic model will generate this graphical model, this data set. So it is indeed a quadratic function with, emphasize, this being our quadratic model, algebraic model. All right, so moving on, let's do a little scroll here. Before getting into the next set of examples, there is an example 5 in the book. I encourage you to take a look. It talks about taking data and creating a scatter plot and a line of best fit, things that you've done with like statistics units in your prior classes. So just take a quick look at that, and then we get into the zero factor property, or zero product property is probably how you've seen it before. So it just mentions that a product of real numbers is 0 if and only if at least one of the factors in the product is 0. So the idea there is that we're generalizing. We don't know which factor would be 0, so any values that would make any of the factors equal 0 would be a solution for that equation. So you have a couple variations of equations. So example 6 gives you what looks like a cubic. So if we set it equal to 0, we can then go ahead and like fully factor it and then get our solutions from our factors. All right, so if we just do some quick manipulation and set it equal to 0, we would have 12x to the third plus 11x squared minus 5x, putting it in standard form, equals 0. Then we have a common factor of x, so factor that out. That leaves us with 12x squared plus 11x minus 5. Oops, weird 0. Okay, so at this point, you now have a quadratic expression that needs to be factored. So, you can do a guess and check method, I know students have kind of studied and figured out a couple different methods for factoring. I've showed you guys using the X to kind of help you organize and factor, so that's also an option. So I'm going to just kind of review that real quick. All right, so if we are going to use the X method to factor this, we can set up an X off to the side, if my screen will cooperate, where we do the A times C to fill out the top. So 12 times negative 5 would be negative 60, and then the B, positive 11, would go on the bottom. We need two numbers whose product is negative 60, so a positive times a negative, and then they need to add to the 11. So we need 11 more positives than negatives. So it looks like that would be positive 15 and negative 4. So again, we would want to use those two numbers to split up that positive 11x into two terms. So we have 4 terms instead of 3, and then we can factor by grouping. So I'll just do that right below here. So we have 12x squared, and then I can use either of these to be next. It doesn't matter the order, so I'm going to just group it as negative 4x and then plus 15x. So again, that sums to be the positive 11x and then b minus 5. So then if I go ahead and group the first two and the last two, I can take out the greatest common factor of each group. So that would be 4x for the first group, and that would leave me with 3x minus 1. We can do positive 5, and that would leave us with 3x minus 1. So the fact that these are matching is good. That's now a common factor of 3x minus 1. And then I have 4x plus 5 is what it would distribute with to make that line above. So let's see if I can fix the screen. All right, so those are our factors. Going back to our main problem, we now have x times 3x minus 1 times 4x plus 5 equals 0. So the zero factor property says any of these three factors could equal 0, or any x that makes any of these factors equal 0 would be one of our solutions. So again, 3 different factors that are multiplying, so we need 3 separate equations to get solutions. So our first one would just be x equals 0, so that's already a solution in itself. The second one would be 3x minus 1 equals 0. And then the third one would be 4x plus 5 equals 0. So if I solve that, add 1 over, divide by 3, we get positive 1/3 as a solution. And the other one, subtract 5, divide by 4, we'd get negative 5/4. All right, so there are our 3 real solutions for this cubic function. All right, example 7 has us working with a quadratic equation this time. So let me make some colors here. So similar process, we want to set it equal to 0. So we would have x squared plus 6x minus 13 equal to 0. That is one option, and you can then try to factor it, but that's already not looking good with having that negative 13. So you would have to do 1 times 13, but you're not going to be able to sum and get positive 6 out of that. So you're going to need to use a different method than factoring for this quadratic. So you could absolutely use the quadratic formula. That's totally fine. I'm going to show completing the square just so you can get review with that, because I know that's the method that students tend to choose the least. but once you kind of catch on to it and relate it to factoring and using the x, it's really not that bad. It's just something that you need to practice enough so that it gets easier. So when you are completing the square, the idea is that we're going to keep the x squared. We want an a of 1, which we already have. We have the plus 6x, or b is positive 6. What we want to do is be very strategic in choosing our c value. So we're not going to use the negative 13. We're going to choose our own value of c. So I'm just going to put a little line to say, all right, I'm going to fill that. I'll go back and fill that in a moment. The negative 13, I'm going to add it to the other side. So equals positive 13. And just know when we add in a c value, in order to keep the two sides equal, we're also going to be adding it in on the right as well. So we're adding in an extra quantity on both sides that's exactly the same to keep the two sides equal. So when you're choosing that value of c, one way to think about it is going back to the x method and just kind of, sorry, I was getting another color. So if we go back to the x, I'm just going to do it off to the side. The idea is we want to factor our quadratic expression on the left side into two identical factor groups. So if you think about how we would fill this out, we don't know the c, so we can't fill out the top of the x, but the b, positive 6, does go into the bottom. And if we're trying to make two identical factor groups, that means the numbers on the sides have to be exactly the same. So the only numbers that we'll add to be positive 6 that are exactly the same would be half of 6. So 3 and 3. And that means the top number, since those have to multiply to make the top number in the x, that top number must be 9. So positive 9 is the value that we want to add on both sides to complete the square. All right, switching back to purple here. So that means this factor on the left side factors into x plus 3 times x plus 3, or just x plus 3 quantity squared. So sorry, this thing is really acting up. And then the other side would add to be 22. So then we are going to undo the square using the square root on both sides. Be careful when you take the square root on both sides, you would have a positive and negative solution for that square root 22. On the left side, the square root would undo the square and just leave you with x plus 3. And then you'd have plus or minus square root 22. And then to solve for x, you would just subtract the 3 over. So you get x equals negative 3 plus or minus the square root of 22. So same thing you would get if you use the quadratic formula, which I know you prefer, but just maybe give a couple problems in your practice a try using completing the square. Just the more you try it and practice it, the easier it'll be. Okay, so just to kind of interpret what those two solutions are, I'm just going to kind of rewrite each of them. So if I do negative 3 plus the square root of 22, I would get about 1.69. And if we do negative 3 minus the square root of 22, we would get about negative 7.69. So these are our two solutions. Our solutions have different terminology. There's multiple names for these depending on the perspective of the problem. So just to kind of clarify, roots versus zeros versus x-intercepts. These values would be, switch colors to make little notes down here. If we talk about these numbers as roots, they are the roots of the equation x squared plus 6x minus 13 equals 0. So we could say these numbers are the roots of that equation where equals 0. If we want to talk about these as zeros, zeros are for the function y. Let's try that again. Y equals x squared plus 6x minus 13. If we want to talk about these as x-intercepts, x-intercepts belong with a graph, so the graph of y equals x squared plus 6x minus 13, squeeze it in there. So just to kind of differentiate, I know we use the words interchangeably, but technically roots are for the equation where equals 0. Zeros are for the function itself, y equals function, and then x-intercepts would be the graph of that function. So just to kind of differentiate between the three. All right, let's move on to the last page. So next we get into some problem solving. So the book outlines a problem solving process that they encourage you to use, throughout the entire book. So step one, just make sure you understand the problem, kind of dissect what it's telling you, what it's asking for. Step two, develop a mathematical model of the problem. Step three, solve the mathematical model and support or confirm the solution. So within these models, you have, the three that we talked about, numeric, algebraic, and graphical. So it's just kind of using whichever is most appropriate or combination of models to kind of verify what you are predicting for the problem. And then step four, interpret the solution in the problem setting. So we have a pretty simple example for example 8. It mentions students are paid 9 cents per mile plus $30 per day to road test their new vehicles. So with just that given information, we should be able to figure out how much what Sarah was paid to drive 385 miles in one day. Also, if Ivan earned $84, how many miles did he drive? So you have all sorts of options of how to go about this. Probably an algebraic model would be the most useful because then we can use that algebraic model to substitute in these quantities in the questions A and B and then be able to get our solutions. So if we have a rate of change plus a constant, that's just going to be a linear function. So if you think back to over the last few years with the Carnegie materials, they emphasized a lot the independent and dependent quantities. So kind of looking at this problem, thinking about those, what would be independent would be your number of miles driven, and then the dependent, as a result, we could calculate how much they're paid. So I'm just going to choose simple variables here. So we can use maybe for miles M, and how much they're paid, use P. And say, all right, if we want to calculate how much they are paid, we need to use the rate of change, 9 cents per mile. So take that rate of change and multiply by the number of miles, plus the constant of $30 per day. And then we have an algebraic model that we could work with that allows us to substitute in either a number of miles or an amount that they were paid. And we have A and B are each of those. So then working with A, she was paid 385, or sorry, not paid. She drove 385 miles. So, I mean, the main thing with these algebraic models is just make sure you're substituting for the correct variable, which is why if you use letters that help you relate to the quantities they're representing, that helps you make less errors. So that's why I did that, P and M instead of like Y and X. So then we're trying to calculate the pay. So it's 0.09 times the 385 miles that she drove, plus the $30 that she automatically gets. Looks like P equals 64.65. Now, something I think is really important with word problems, and this is the step 4, is interpret the solution in the problem setting. So not just saying P equals 64.65, but what does that mean for the scenario? Just putting like a quick little statement. So Sarah was paid $64.65. All right, and if we do something similar for Ivan, we are given the amount that he was paid. So this time we have the B value, 84, and then we know it's 0.09 times a number of miles that we don't know yet, plus 30. So in this case, when you don't know your independent quantity, it's just a couple of extra steps to solve for it compared to, example A. So if we subtract the 30 over, we'd have 54 equals 0.09 m. So if we do 54 divided by 0.09, it's exactly 600. So then we can conclude that Ivan drove 600 miles. Oh, there we go. All right, so just choosing the model that kind of best works with that problem. So in this case, an algebraic model. All right, so after example 8, I would like you to go back and take a look at examples 9 and 10 in the textbook. They talk about just ways that when you are graphing functions, how technology could kind of on the surface seem to fail you. Like example 9 is grapher failure, and then example 10, not seeing hidden behavior. So it just kind of goes over some of the things that you need to be aware of when using technology to graph functions. The most common one would probably be that you need to adjust the window of your of what you're viewing of your graph. Maybe adjust one or both axes so you can see the entire graph and it's not cut off. Just something simple, but just go ahead and browse through that. And then we get into our last problem, which, as we're talking about modeling, one thing that's really important is deductive reasoning. So using a logical sequence of algebraic steps to show that something is undeniably true. So this essentially leads us to the idea of proofs in math. Example 11 wants us to prove that 6 is a factor of n to the third minus n for every positive integer n. So looking at positive integer values of n. Okay, so students' instinct might be to test this out and say, all right, I'm going to choose values of n, and I'm going to substitute them into n to the third minus n, and I'm just going to test it out and see what happens. So if I start with the first positive integer, that would be positive 1. If I substitute that in, 1 to the third minus 1 would be 0. 6 would be a factor of 0 because we're trying to prove that 6 is a factor of any result that we get by substituting in a positive integer n. So 6 times 0 would make 0, so that checks out. I'd go to the next positive integer, 2. 2 to the third power minus 2 would be 8 minus 2, I would get 6. So then I do get, that would be a factor of 6. Going to n is 3. 3 to the third power is 27. 27 minus 3 is 24. 6 is a factor of 24, so that works. So looks like the first couple are checking out fine. Maybe I want to skip ahead a bit. Maybe I'll go to, say, 10 and do 10 to the third power minus 10. That would be 1,000 minus 10, so that would be 990. And if you divide that by 6, that does divide evenly. So 990 is has 6 as a factor. So we could do this forever because obviously the list of positive integers is infinite. So one thing that we learn very quickly in math is you cannot do proofs by using specific numbers because just because we have a couple examples that work doesn't mean that we know for sure that it's undeniably true that 6 will always be a factor of this n to the third minus n. So what we need to do is generalize the idea and use models that will work for any value of n. So let me kind of switch up colors again. So let's take another look at that expression n to the third minus n. If we do some manipulation here, we have a common factor of n that we could factor out. And if we do that, we would be left with a quadratic n squared minus 1. Since that's a difference of two squares, we can factor that even further. So we can factor this down into all linear factors. We would have n plus 1 times n minus 1 for that difference of squares. And now I want to just take a closer look at these three factors we now have. We have n, which is just going to be some positive integer. If you take n and add 1 to it, you have a factor that is 1 greater than n. And then n minus 1 would represent a factor 1 less than n. So if I just reorder these, I would have from least to greatest, n minus 1 times n plus 1. So you have three consecutive numbers, three numbers in a row, represented by these factors. So this is already very close to what we want. One thing I recommend when you're generalizing is you can always pause and take a moment to then just kind of break down some examples of three consecutive numbers and look for patterns. So basically like a numerical model from this point. Sorry, I'm trying to choose color here. Let's go with this light purple. So if I think about three numbers in a row, I don't know, let's say 9, 10, and 11, or maybe 20, 21, 22. I'm just choosing a couple examples. Or let's go with small numbers even of 2, 3, 4. And if I'm just kind of looking for patterns from one set to the next, I know because I'm talking about consecutive numbers, I'm either going to have two odd numbers with an even in between or two evens with an odd in between. But regardless, there's going to be at least one number that's even. That means for these three factors, at least one of them is divisible by 2. So if one of these factors is divisible by 2, then multiplying them into n to the third minus n is also going to be divisible by 2. So I'm going to make a note. 2 is for sure a factor of n to the third minus n. All right, what else? If we explore this, let's go a factor higher than 2. Since it's three numbers in a row, let's think about a factor of 3. Like looking at that first example, 9 can be divided by 3. In the second example, 21 can be divided by 3. And the third one, 3 can be divided by 3. So because your numbers are, you have three numbers in a row, there's always going to be one that could be divided by 3, making 3 a factor of the overall expression n to the third minus n. So 3 is also a factor of n to the third minus n. And the way factors work is you can multiply factors together and get larger factors of your expression. So since 2 times 3 is 6, that means 6 is, do another line here, 6 is a factor of n to the third minus n. So we just proved using algebraic models and numerical models, just the idea that you have these three consecutive numbers in your factors of n to the third minus n, that 6 will always be a factor of n to the third minus n. So again, we can't prove that is true by substituting in values of n because we could never exhaust the list of what's every positive integer n, but this algebraic model breakdown will prove that that will always be true. 6 will always be a factor of n to the third minus n. All right, so make sure that you have read through the lesson, and then you can go ahead and start looking at the practice problems or wait for us to go over this in class.